Visible is something that you can, is a rainbow color, the visible is light, so you already know about that. And infrared is the electromagnetic radiations with the wavelengths and specific reasons in the red box here. It's that is shorter than microwave sensors, but it is longer than visible microwave length. Um, the thermal infrared sensors measured it naturally emitting emissions from the target in the specific region that I just mentioned, and their specificity is largely depend on the target's temperature to be measured. However, there's an atmospheric window, like I just explained before in the beginning. So we don't just use entire range of infrared sensor. We just select the specific reasons which must be transparent, and free from atmospheric opacity due to observations. So these are this band wavelengths for the Aster and Moody's and Landsat and so on. They use their own specific, clear, transparent regions so that they can freely, cleanly transmit and receive the signal directly from their sensors. So when we retrieve vegetation property from these thermal or optical sensors, we use and combine several different bands because specific pigments in the plant leaves strongly observe some specific bands like a red light. However, strongly reflect near band, near infrared bands. So if we combine those bands, observe and reflect bands, we can make a better specificity to the chlorophyll contents. So vegetation index can be, suggested. So from this vegetation index, we can estimate timing and extent of the drought because, under drought, vegetation will go brown and lose chlorophyll content so that we can pretty much interpret that, oh, okay, something, drought is going on there. And we want to relate those indexes with fewer moisture contents or in evapotranspiration. However, this approach also have several limitations. There is a saturation problem. Saturation means although evapotranspiration goes up and up and up, or the temperature goes down and down and down, just LAI or NDVI just stay similar, like 0.5 or 0.7, doesn't really go up largely. And second problem is that it's difficult to apply to forests. Like forest is, usually, like 20 meters tall, but the crop is, only just 1 or 2 meters high. But their NDVI or LAI is sometimes very similar. Like if you measure LAI for the corn, let's say if that is 4, and the huge like pine tree, like 30 meters high, like gives you, just a 4 of LAI or something like that. So it does not really differentiate, does not really give the properties specifically for the forest. And the relationship with soil moisture, fuel moisture is quite often very weak. And although it is non-drought situation, but still you can lose chlorophyll contents, like when there's a disease or infected by pests, or if the trees and forests are aging or deciduous leaf flushing, and they may lose chlorophyll contents, but that doesn't necessarily mean that their vegetation moisture is getting dry or they are under drought conditions. So this is something that you have to be careful very much in making interpretations. And another limitation using shortwave infrared sensor is that reflectance itself can be affected by a different properties, which is not really about the fuel moisture. So they can more affected by vegetation structures or atmospheric conditions like a cloud or smoke, something like that, more than the pure moisture. And another limitation is that they are using empirical approach. Like we just discussed in the previous slide in here, the nonlinear effects at the larger scale is not something that you can easily conveniently rearrange or reproduce with laboratory scale experiments or empirical relationships or spatial averages of point-based measurements, and is really hardly be directly extrapolated. However, if you apply the empirical approach anyway, then that empirical relationship would perfectly fine to the pixel that you carried out your experiment or validation work. However, if you extend that application to the other pixels with the different features, those estimations, totally can be, nonsense, right? So these are just example. If you look at the right hand side, this is NDVI images, and the red contour here is actually the fire burned area. However, before the fire occurrence, this NDVI did not make any warning that this area will experience and ready to trigger ignitions or ready to ignite huge amount of fuels. They were just more green than adjacent areas. So this can happen. LAI, it's more complicated to retrieve LAI from reflectance and thermal infrared bands. They categorize the lens biomass into 6 or 8 different biomass and parameterize their relationships and vegetation properties. Like they divide into like grass, shrub, broadleaf birds and so on, and then they try to parameterize the pixels differently by those biomass. So they use lookup table approach. Lookup table based procedures will exploit spectral informations from the red bands and the near infrared bands, and with this backup algorithm would also use empirical relationship with NDVI and the canopy LAI and so on. Which also would require several different type of inputs, including vegetation structure and so on. So if you look at the figure here, it's quite interesting that the NDVI indicated by B column here in the center, which does not really go together with leaf water potential on the bottom indicated by C here. They don't really, there's no really good match or correlation between them. For your information, leaf water potential is the measure of the amount of water available in a plant leaves. So by theory, we expect they would have a positive correlation, but it turns out that it's not really clear. There's a potential reason, and possible reasons must be something that we already discussed, that it's more specific to the greenness rather than moisture. So there are other options that we can do with thermoinfrared sensors in a different wavelength regions. One of them would be retrieve land surface temperature to hopefully indicative of fewer temperature. And we would like to look at water stress forests or fewer moisture contents out of land surface temperature. And actually land surface temperature is widely used for the estimation of fewer moisture contents. Is usually one of the input for the estimation of fewer moisture contents. And they are often used for the fire weather index and also use it for the estimation of evapotranspiration, because when the water stress goes up and stomata closer, there will be stomata closer and latent heat will decrease. So there's some correlation. We hope that there will be correlation between water stress and latent heat and evapotranspirations at land surface temperature. However, there's a limitation as well. That's too sensitive to weather conditions. For example, if there's a rain event, not really intense rainfall. However, there's a rainfall and then a temperature just suddenly drop. Although the fjord or forests are not really experiencing those cooling effect immediately. And to estimate evapotranspiration, to estimate evapotranspiration requires more other variables such as aerodynamic temperature or canopy height information and so on, but usually those informations are not available, which propagate errors to estimation of evapotranspiration or land surface temperature. And when we apply land surface temperature to forests, which actually has more complicated procedure to make accurate, reliable estimations, because there's additional radiations and clumping factor or something like that, which is also very complicated to reliably estimate. And although LST is reliably estimated, sometimes there's a weak relationship with the fewer moisture contents. Yep. So if you look at the right-hand side, this figure shows the relationship between burned area and the land surface temperature, and the relationship is kind of scattered, right? And this is about the modeled land surface temperature. When we use satellite land surface temperature, if you look at on the right hand side here, although we are using satellites sensors that can be still inhibited by clouds and smoke and dust or standing water or snow like that. And there are, like we discussed it earlier, there are hydrological factors, but these are not considered for the measurement of forest emissivity. Instead, which is assumed to be linearly related to a function of NDVI. So these are all the source of uncertainty. So another options available for fire predictions is passive microwave sensors. Passive microwave sensors target a little bit longer regions than the infrared or visible sensors. So this is here. However, there's still a window of opacity. There's atmospheric opacity available for these regions. So we really have to narrow down to the atmospheric window regions with a low opacity, which will allow the transmission of electromagnetic wave radiations As compared to optical or infrared sensors, there is technical advantages when using microwave sensors. There's almost no interference as compared to, relatively, as compared to infrared sensors. So they can penetrate through the clouds, dust, smoke, snow, and light rain. When there's heavy rain and snow, they are affected. So we can say that it's weather independent. Unlike active microwave sensors, passive microwave sensors measure radiant energy from the Earth, emitted and reflected from the Earth. So they don't really send any pulse or signal and reading, returning signals and so on. They don't send any energy. They just measure naturally occurring emissions from the Earth. And radiant energy is converted to, biophysical quantities and physical variables. That's something that human can understand and better, easier understand, which would be, for example, temperature, rainfall, soil moisture, and so on. However, they use the same principle with the thermal sensors, and they can use multi-frequency, multi-polarization, like, VV, HH polarization, VH polarization, and so on. However, they have a weak energy source, so need a large antenna and instantaneous field of view and wide bands. I will going to explain this better. And the Planck law is basically the passive radiometers applied to investigation of land surface involves the detection of thermally generated radiation from the surface at the microwave frequencies. And these spectral bands where passive microwave radiometry applies is actually longer than the infrared sensors. But still relies on a Planck radiation law. If the temperatures to be measured lie in the vicinity of this, although this is 5,000 K, like around 300 Kelvin, it's around the Earth's surface temperature, and the radiations of the interest can be approximated by Rayleigh and Jeans approximations. As you can see in here, in here, can I, in here, Rayleigh-Jeans law, linearly approximated as Rayleigh-Jeans approximations, and this is the function of the temperature. If I zoom in this area of passive microwave wavelength regions, and passive microwave sensors operate in low energy tail in here, at a longer wavelengths of the black body radiation curve for the temperatures in the region of in here. So signal received at the radiometer antenna is extremely weak. So they need a relatively large antenna beam width is required to collect enough energy to yield a detectable signal. So like I said several times in this session, passive microwave radiometers are, usually characterized by low spatial resolutions because of this spectral property. So like I explained, there was a linear approximation for the Planck law brightness temperature is, brightness is directly proportional to the temperature of radiating source. These approximations above is applied to the ideal black body. So the reason that I'm describing the theory basic principle is to explain the definition of brightness temperature, because microwave radiometers measure brightness temperature. So what is brightness temperature? Brightness temperature is that something that is emitted is equal to the temperature of equivalent black body. Black body has the emissivity of number 1, and perfect emitter and perfect observer are just ideal materials. And so brightness temperature is linearly related to the kinetic temperature of the surface. And brightness temperature in this equation, as expressed by this equation, is the temperature that the black body would have to have the same brightness at the specific frequency as a gray body, with emissivity E and temperature T, right? So emissivity is a measure of how well a material surface radiates the energy or the ability to emit radiation. So emissivity is the temperature. If you have brightness temperature and physical temperature, and you can pretty much estimate emissivity. And these are the examples for the passive microwave sensors. And SMOS is launched by ESA in 2009, and they have this sensors, MIRAS, radiometers that operates at the L band, and AMSA-RE operates at X band and also C bands, although there's some RFI, infrared interference, and their resolution is 50 kilometers. And also there's SMMR, which is available at 6 C bands, and their spatial resolution is much lower at higher than 100 kilometer. And active microwave sensors also can be applied for fire predictions. Unlike passive microwave sensors, active microwave sensors apply their own energy source. So they send the pulse to the target and reading the returning intensity from the target. So most active sensors operate in the microwave portion, and where the atmosphere is usually transparent, so that we can get the signal during day and night, which is quite different from infrared sensors. That's a technical merit. So it can be applied to meteorology and land surface detection of land surface, and examples include altimeter, LiDAR, radar, scatterometer, sounder, and so on. And there are various kinds of radars, like synthetic aperture radar, rear aperture radar, depending on how they construct their radar antennas and how they view the ground, and whether the polarization is cross polarization or multi-polarization or single polarization, or whether it's VV or HH or HB, VH, and so on. And the sensor can be single or multi-band systems. The important thing is that It's important to know that L-band would have here. L-band, their wavelength is longer than Ku band, and their resolution is lower than Ku band. Antenna must be larger than Ku band. That's all about the wavelengths and the frequencies. So if the wavelength is different and their penetration behavior is also different. Although the pine tree is same, if you using X-band, which is short, wavelength is very short, and then then the signal is usually scattered on the surface of leaves. So you are going to detect the moisture from the leaves. But even before reaching the leaves, they are very sensitive and scattered by vegetation structures and many other factors. But if you have a longer wavelengths, like L-band or P-band, then they get penetrate through the leaves and even enter the branch, yeah, even to the trunk. So these are the targets that they are actually reading. So depending on the wavelengths, the parts that you are going to read from will be different. The active sensors can be largely classified into two groups, non-imaging and imaging. Non-imaging is usually just one linear dimension, just poop, 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 yeah. So they just measure something like, for example, like altimeters. They measure the distance. So short microwave pulse is transmitted towards reflected back by the target, usually right beneath the sensor. So distance can be, distance to the target can be measured by as a function of time, how long it takes to get the signal, right? And the scattorometer is also a non-imaging radar. Their properties of the surface and vegetations can be measured from backscattering, cross-section. However, imaging radar sensors can measure two-dimensional or three-dimensional measurements. As you can see the figure here on the bottom, they are moving. They have a large angle, view angles, scanning, two-dimensional large areas with the view angles. And the SAR is actually applicable to this imaging radar. So antenna emits the signal in the beam towards the target and then receives back their backscattered sign from the surface. So what does it measure? I just mentioned the terminology of backscatter, right? And then in this slide, we're going to look at what that is. A radar can measure amplitude. Amplitude means the strength of echo reflected back. The strength of echo reflected back from the target. If you look at the right hand side, you send the signal, and then the pulse returned back to the sensor and antenna. The measured reflected echo. And the phase, and radar can measure the part of the echo reflected back towards the antenna. This is backscatter. So the strength of reflected echo is backscatter ring coefficient, which is expressed by sigma naught, and unit is decibels. They are a function of roughness, dielectric constant, geometry, instrumental configuration. Instrumental configuration means whether they're VV polarization or VH polarization, whether their view angles are 20 or 40 degree, or what view angles are used and so on. So that is received energy over energy reflected. So negative value of backscattering coefficients means it's more focusing on the backscattered energy away from the radar. However, it is the backscattering coefficients to extract information from backscattering coefficient is idempotent problem, meaning there are so many complicated combined factors that affect intensity of backscattering coefficient. So if you look at the figures here, if it is smooth and just open water and or road, it is just dark. I mean when there's a moisture, it is whiter, but yeah, okay, let's delete the water, open water, yeah. When it is smooth, it can be dark, but when the surface is rough, and for example, like a tilled agricultural fields and so on, or when there's a water, soil moisture and so on, it becomes brighter. But there are more other factors to make it bright, like a topography, or if there's a rocks or vegetations or and so on, then it also contribute to the brightness. So that's not really simple, and we can't really jump into the conclusion, okay, this is brighter because of roughness. That's no. So that's why we say it is idempotent problem. So radar and SAR has a higher resolutions, like sometimes 10 meter, as compared to passive microwave sensors, which is available at 25 kilometers up to 120 kilometers. However, SAR is very tricky sensors and it's very complicated to interpret. So simple interpretation or linear relation is not really recommended. Although it is high resolutions. One example of SAR is ASAR. It's launched by ESA. They operate at C-bands, and 5 different polarizations are available. Their spatial resolution is 30 meters to wide swath mode. And their swath width mode is available up to 100 kilometer, or wave mode would be 5 kilometer. So at the global monitoring mode, it's 400 kilometer is also available. So if comparing active and passive microwave sensors, it's also would be interesting. So basically, passive microwave just measure the emitted microwave energy from the sources. However, active microwave sensors send and receive electromagnetic pulses from the target. And in case of active microwave sensors, their information could come from discrete levels. Yeah, because they send the pulse, and then receive the signal in a discrete mode. So their information returning can also be like that. Passive microwave sensors detect, estimate sea surface wind vectors and salinity, like active microwave sensors. Men better at estimating atmospheric temperature and moisture profiling. However, that is not applicable for active microwave sensors. And however, both sensors are available to be applied for the estimation of soil moisture and surface wetness and roughness. And passive microwave is better at estimating vegetation water contents and land surface temperature. Active microwave sensors is better at vegetation structure and biomass, land use, surface roughness, topography, and geology, and so on. Passive microwave sensors can be applied to sea surface temperature, while active microwave sensors can be applied to ocean surface topography and surface state. Okay, that is pretty. Thank you very much for your attention.